Okay, finally I can see that this whole thing is working. Yesterday I recorded a stream as usual, but it just never started working. So I don't know what was going on. Okay, let me close that. Sorry, I'm a little bit disorganized today, and I also don't have a lot of time. Let me find the problem for today. Okay, it's the last one in a series of 10 plus hard problems that I wanted to solve. Okay, let me share the screen back. Here, this, and change the layout. Let's go. Word break 2 sounds like a fun problem. I already feel that it's something dynamic programming, like word and breaks. Yeah, yesterday actually reviewed, the day before yesterday I reviewed what I was doing, and oh no, yesterday you haven't seen this, but I was solving another problem and I wasn't able to figure out how to do the dynamic programming part well, at least. So that was not a good performance from my side. Okay, string s and word dictionary. So dictionary of strings. Oh, I'm assuming it's just a set of strings as bases in string s to construct a sentence where each word is a valid dictionary word. Return all such possible sentences in any order. Okay, so we are returning sentences, add spaces. Okay, so we are adding spaces and returning strings. So we will be returning a list of strings. And tests. So we have a string s, which can be the usual example of string a, b, c, d, e. And then we want to do a, b, c, d, e, b, c, d, e, c. And here we will be returning what? We will be returning a space b, c, space d, e. And we will be returning a, b, c, d, space e. So those are the two sentences that we can compile from these substrings of this word. Okay, this problem is actually very similar to the one that I was solving yesterday. I will not be spending too much time here, but yeah, one of the things is that brute force is try all possible combinations of substrings, which is kind of what we will be doing, but probably we will also add some memorization and it would simplify things for us. But this would be of 2 to the power of, let's define things a little bit. Let's say that we have m letters in S, then it will be 2 to the power of m runtime, and of n space where we have n words, word dict. It's like it depends also on like how many letters are on average in, let's say, k letters on average in Word. So then it will be off in key space. Because what we will be doing here, we will start with the first letter, and then we will check if this first letter is in the words list, words ticked, sorry. Oh, actually, this is given to us from the input. So this is not auxiliary. Then let's think about this problem. Okay, so if we do recursions, it will be also up to the 2 to the power of n recursion. So yeah, it will be of m space for recursions, because we will not be doing many recursions at once. We will only possibly have one recursion at each letter of this word. So what I mean by recursion, right? So we try to fit this part of the word and we try to match it to something here. If we are able to, if we succeed, then we basically need to solve the same problem on the rest of the string, on the suffix of the string. And we mostly will do m recursions, but the problem is that if we don't succeed here, or if we do succeed here, we either way we need to populate our sentence, and then we try another combination. So we will try to do a plus b and then continue here. So how to improve this brute force, and the thing that I couldn't figure out yesterday, I basically wrote the whole thing, but it's kind of obvious that, let's say you start with A and B. Let's say that you also have something like B here. And yeah, so this doesn't change our result. But then what it changes is that we first start with A, and then there are two choices for B. So we match the B and we try to find the next match for like all the rest of the letters here, like C, D, E, for example. But then let's say we also have AB, right? So then if we try it first, like as A is a separate letter and then B is a separate letter, and we then have to match if there is a CD option, then if we do it AB, then we will have to do the same job again here, figuring out if there is a CDE matching combination of words. So then we don't want to do that. We can just memorize everything, the rest of it, and this will work fine for us. So yeah, I will do recursion with memorization, and because of that, the recursion calls will be at most like M. So recursion with memorization of M recursive calls, and in each of those up to of M operations in each, and then we also need to do matching. So we need to do matching for this letter. So we will need to basically search for K letters. So it will be O of K to find a match in word dict. So it summarizes to O of M squared and times km squared. Runtime and of M space. So let me do the implementation for this. Yeah. I'm solving this easy today because I solved pretty much the same problem yesterday, but it was instead of this, where we are splitting the word, it was instead we have a list of words and we want to try to concatenate words in our dictionary and get some words from the list. So it was pretty much the same problem. Okay, let me think about how I should be implementing this. So let's say that we will kind of do depth first search in our recursion. So I will call it DFS, and I will start at I of our word, and fortunately we have just one word here, one S string. So this will be an integer starting index, and it will return it will be returning none. We don't need anything there, and the only thing that we need is to modify answer if we succeed. Okay, so how do we figure out the final step? Yeah, so if we get to the length of our string s, we would write our DFS function in such a way that we can only get to I equals length of s, only in the case when there is already like a populated the fully matching sentence. So I will also add current sentence, which is this. We don't want to do operations on strings each time, so we will store it as string up to the moment when we publish it in our answer, and then return answer here. But first we'll need to do DFS of 0. Okay, this is interesting. We are not actually giving word dict. We are giving a list. So we will need to modify that, and that would increase our space to O of nk. But we basically need to check quickly. Oh, dictionary, yes. So dictionary is not in the sense of the data structure, it's dictionary in the sense of like vocabulary. So let's do vocabulary equals set of word dict. And we can reuse the same word again and again, I'm assuming. Yeah, the same word we can be reused multiple times in the segmentation. So we don't even care if all the words are unique or not. If they're not unique, either way they can be used several times, so we don't care about that. Okay, so this is it. The only last tiny thing that we have to do is to implement this DFS, and we will also have to do LRU cache here, so that we don't start, like when we get to a specific I, we don't want to start again from scratch there. Okay, so now how do we process this? So DFS, we are doing at index 0, and then we need to is to add letters starting at I one by one. And okay, first we need to do this. If I equals to length of s, then we do answer append current sentence, but we need to join it like this. So then we will also need to be careful about adding or removing pieces into our current sentence. Okay, so while I is smaller than length of s, current word, actually we only create current word if we are not returning, so let's do it here. Current word append s of I, and then we are checking if I might have to also check my running time because this operation will be of k, but yeah, of k to join and then O of k to search. So we already counted it. Like doing the O of k operation twice doesn't change our running time. So then if this join current word in vocabulary, so if that's the case, then we want to try and match this part of the sentence. So now I will be pointing to the last letter of this current word, and we have just added it to the current word. So what are we going to do? Let's do this. So word join word equals this. If joined word is in vocabulary, then we do several things. We first update current sentence, append joined word, and then we try to do DFS of I plus 1 at this point. And then once we return from there, we'd want to do current sentence pop. Whatever happened in this DFS, whether if we were successful in creating a new sentence, we have appended it to answer. And now we want to go back and consider other possible options. And if we weren't successful, then we just return here and try again with other combinations of letters. Okay, so if joined word is in vocabulary, blah, 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 and now we need to do I plus or equals 1 so that this loop ever ends. We don't need to return anything, I think, yeah, so we just need to be careful with our current sentence. And current word, it will be defined each time in each DFS function, so it will not be it will be individual for each scope, so we don't need to like pop any letters from the current word. We just append until we get to the end of the sentence. Sorry, to the end of string S. Yes, I think this is a fine solution that should work. Now let me check this, but let me check it on some simpler example. So let's say we have a string ABC, and then our letters are D, doesn't matter, we are basically never going to match this. Then we have AB, and then we have C, and then we don't care. Okay, let's also do A and B, so that there are two sentences that we need to output. LRU cache DFS, so we are doing the first call at index 0. And this index 0 isn't equal to length, so we continue here, and the current word is empty. So for this current word, we try to append the letter A. We are appending letter A, and then joined word becomes A. And if joined word in vocabulary, then the current sentence becomes also A. Oh, what I have forgotten. I have forgotten spaces here, right? Yep. So the current sentence comprises of words, and we need to add spaces. So the current sentence, yeah, the answer will need to have spaces. Current sentence doesn't have spaces yet. So current sentence is actually a list, so it will be A, comma, and then we go fold one line here, and we continue to B. So we are doing another call at index 1. So for index 1, it's still not the length of string S, which means that we are just going here. And then on this call, the current word becomes B. And yes, we have updated it here. We joined word is in the vocabulary. So we are now continuing and trying to make another call here, which is, oh yeah, we also need current sentence append current sentence B. So now we are making the same call, but at index 2. And the current index becomes C. And C is in the vocabulary. So we append it to the current sentence and we jump to the next index, which is finally index 3, which is the length. So answer append this, join current sentence. So A, B, C, because we are adding spaces everywhere. So this is our first possible answer. Then once we did that, answer append, oh yeah, we should be returning, obviously. Well, it would work either way, because we will just not get into the loop and return either way, but let's make it explicit that we need to return here. And now current word, so we are returning from the last, so now we are at this level, at the level of C, so in this function. So let me maybe say that this is processed. And then we go back and we are at C, and we are now current sentence pop. So current sentence, we remove C, and then we try to continue, but we get to the end of the loop. So we are out of here, out of this function, and it means that this one becomes processed. So call it at index 2 becomes processed. Oh, yeah, this is incorrect implementation. I need to be returning the words themselves. Otherwise, I'm not kind of returning anything, right? So what am I caching? I need to cache what I'm returning. Yeah, so this won't work because of how I implemented this. We now need to change that instead of this none, it will be returning a list of strings. So yeah. So if I want to return all possible combinations, yeah, I think I will have to do something like okay, so instead of doing this, let me actually create a different thing. I will create a new function just below. I just have 7 minutes left to work on this, so let me try to be quick. So DFS, it needs to return list of strings. How do we process this? So it means that when we have a specific current word, we try to get, we don't have this anymore, but we have this here. So next words equal okay, so for current word, damn, no, I cannot do that. I need to do that on the last step. So what I wanted to do I thought about, let me just return everything to the start of the function. But if we are returning to the start of the function here, like onto the first level of our DFS call, if we are returning to this level, we will not be able to add these sentences to the answer, because we will be adding basically just the first sentence we are returning, and we will never go continue and like try other possible directions. So this doesn't work. We cannot do this kind of memorized DFS approach. So instead, we will have to do some bottom-up approach to down doesn't work. Need bottom up. Yeah, actually, I need to figure out if there is even a way to. Okay, I think it is bottom up, but it's bottom up not in the correct way or something. Yeah, we can kind of start returning list of strings. Yeah, I think it should work. So list of strings. Yeah, it will now become quite an extensive thing in terms of space. But yeah, let's do that, I guess. So if we start returning list of strings. Oh no, I didn't want to change this function. I need to change this function, so it will start returning list of strings. Next combinations will be DFS. So combinations to return equals a list. So for combination in next combinations, we will do combinations to return append joint word plus next combinations. Okay, and then I plus 1 here, and then return combinations to return. I don't have time to check it because I basically need to drop off in 3 minutes. So yeah, the problem is that my output is always empty. Yeah, because I'm not returning anything. All combinations equals DFS of 0. Return space join combination for combination in all combinations. So this okay, we are closer. We should be returning combinations. We do have some cache. These combinations. Oh yeah, we still need to have this final thing with So what's the problem? We're returning combinations to return. We are adding, but on the last step will be next combinations. And when we do for next combinations to return, append. So if I equals length of s, this is not a very elegant solution. Return empty list. No, not return empty list. Return a list with one empty list inside. Print all combinations. Okay. I will need to drop off. Okay. I'm pretty close. Oh. Yes. Finally. This might require storing too much. Okay. We have succeeded. It was a tricky problem. Yeah, I probably should have created some table that we can start populating, and here I have created a solution that would require theoretically a lot of space to store all the possible combinations out from the future. But since we have to still join those combinations and combine them and concatenate them, then the space will still be the same as the space that we need for the answer. So we can assume that this will be doable if the problem is solvable at all. But I don't really like my solution. It's definitely not elegant. And this is the first time when I had to jump through such hoops to do things correctly with DFS. Good to learn today. But thanks everyone. Let me stop sharing my screen. See you tomorrow. Bye.